Okay, Steve, time for you to be silly. Bum bum ba da 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 dum bum ba dum bum bum ba ba da da dum bum ba da dum ba dum bum bum ba dum bum ba da da dum bum 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 ba dum ba. Shouldn't have done the split. Shouldn't have done the split. Okay, guys, here we are. Our last quiz. Quiz 12. Woohoo! The end is near. The end is near. We've learned all the important ideas. And now it's time to practice our last set of ideas. All right, so let's start with number 1. Oh, come on, number 1. Here you go. Find the Taylor polynomial for f of x, which is tangent of x, centered at x equals 0. Okay, so that's not so bad. Now, so Taylor polynomial, we're not finding the Taylor series, we're after polynomial. So how do we do it? Well, order 3 means we're going to go through the third derivative. So we have our function, and we're going to be patient with our derivatives, of course. F prime of x would be what? Well, derivative of tangent is secant squared of x. All right, well, that's not so surprising. F double prime of x. Well, all right, chain rule, right? Because secant squared of x is really the same as secant of x quantity squared. So the 2 comes down, then you get secant of x to the 1 times the derivative of secant, which is secant times tangent, secant x tangent x. Of course, we can write that as 2 secant squared x tangent x. All right, now remember, third order, right? So that means third derivative. So what's the third derivative? Well, 2 times the derivative of secant squared. Now, we know what the derivative of secant squared is because we just took the derivative of secant squared. So 2 secant squared x tangent of x times tangent, right? And then we're going to add, now it's 2 secant squared x times the derivative of tangent x, which is secant squared x. Or, if you like, we get 4 secant squared x tangent squared x plus 2 secant to the 4th x. All right, good. So when you're looking for a Taylor polynomial, if it's not a modification of something you already know, you can start by saying, well, let me take the derivatives. Now, we're not done yet. Now, the next thing to do is we're going to take those derivatives that we've just found, and we're going to do what? Well, we're going to go to where we're centered. We're centered here at x equals 0. So, what would we have? Well, we need to know what is f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. Now, it helps to know what's happening at 0 for our functions, secant and tangent. So, tangent of 0 is 0. So that's good. That means that's going to be a 0. Secant of 0 is 1. So, secant squared at 0 will be 1. F double prime, we're going to get 2. 1 squared, 0. Put that together, you get 0. F triple prime, we're going to get 4 times 1 times 0 plus 2 times 1. So that's 2. So those are our derivatives up through the third derivatives. Now, we're not done yet. The last thing is to put it all together. So in general, what we have is our Taylor polynomial will look like the sum from where we start up to some ordered derivative. Now, see, the Taylor series would be infinity, but here we're going to stop. Then we're going to have our kth derivative evaluated at the center times x minus a to the k over k factorial. Now, in our case, a equals 0, so, and we're only going up through n equals 3. So this would translate into the 0th third of the function at 0 times x minus 0 over 0 factorial, which is just 1, plus the first derivative evaluated at 0, and then it'll be times x over 1 factorial, plus the second derivative evaluated at 0, then it'll be x squared over 2 factorial. So x squared over 2 plus the third derivative evaluated at 0. Whoops, I'm running out of space. My page is almost... Okay, well, we'll make it work. Then it's x cubed over 3 factorial. Not 3 factorial, which is 6. Now, we know what these values are because we just wrote them down. So, for instance, here, we're going to get that this is 0, 1, 0, and 2. You might notice that we're seeing this sort of behavior where the even powers are 0, and that's because tangent is an odd function. So whenever you have an odd function, you should expect anything attached to an even power will be 0. You should only be left with even powers. So what's left? Well, we get a 1 times x, which is x. Then we get a 2, and it's multiplied by a 1 6. Remember, the 6 is downstairs. It's not 2 times 6, it's 2 over 6. So that makes a 1/3 x cubed. And that's our approximation. So in other words, x plus 1/3 x cubed does a really nice job of approximating what the function tangent of x does near 0. All right, now before we take this away, let's look at number 2. Because number 2, it's sort of insightful to compare. It looks almost identical. Find the Taylor polynomial for f of x equals tangent of x forward 3 centered at, and here's the difference, pi fourths. Okay, so the only difference is we're shifting where our center is. Will that change our answer? Well, yes, it will change our answer. But it won't change the process. So what do? Well, we do what we did before. Namely, we go through and we find our derivatives. So here we have still our derivatives up through our third derivative because we're doing order 3. Now what we're going to do is instead of finding our derivatives at 0, we're going to do it at our center. And remember, we said our center is at pi fourths. So we want to find the following. What is f of pi fourths? What is f prime of pi fourths? What is f double prime of pi fourths? And what is f triple prime of pi fourths? Now, to do this, it might be useful to remember a couple of things. Namely, tangent of pi fourths, we know that that's equal to 1. And secant of pi fourths, this one we probably know by now. Do you remember what it is? It's closely related to cosine of pi fourths, if that helps. It's square root of 2. All right. So, tangent of pi fourths is 1. So that's our first one. Now, secant of pi fourths squared. So it's square root of 2 squared. So we get 2. 1, 2. Aha! There's a pattern there. Maybe the next one is 3. Well, maybe. Let's see. It'll be 2 times square root of 2 squared. So that's 2 times 1. That's not 3. But it's 2 times 1, which is 4. Aha! A new pattern. Maybe the next one is going to be 8. Well, maybe. Let's see. We're going to get 4 times 2, because we're going to get square root of 2 squared, times 1. So this will be 8 plus 2 times 2 times 2. So secant of the fourth. So we take square root of 2 to the fourth. And so what is that? Well, okay, so we get 8 plus another 8 gives us 16. And that's our derivative, 16. All right, now what? Well, again, it's the same philosophy. So this is our Taylor polynomial centered at A. So in our case, we're going to get, it's going to be the 0th derivative at pi fourths times, times 1, right, because it's to the 0 power of 0 factorial, and plus the first derivative at pi fourths times x minus pi fourths to the 1 divided by 1 factorial plus the second derivative at pi fourths times x minus pi fourths squared over 2 factorial, and then plus the third derivative, because we're third order. Our third derivative at pi fourths, x minus pi fourths cubed, whoop, there we go, over 3 factorial. All right, now let's plug in what we know. We know we have a 1, a 2, a 4, and a 16. And 3 factorial, by the way, is 6, and 2 factorial is 2. 1 factorial, we know that is 1. So when we put this all together, what do we get? Well, we're going to get 1 from the first term, plus 2 times x minus pi over 4. Then 4 divided by 2 is another 2, x minus pi over 4 squared. Then we have 16 divided by 6. Well, they both have a 2 in it, so we can pull that out. And then we have an 8 thirds x minus pi over 4 cubed. And that is our answer. You'll notice here it's a little bit different. It definitely looks a lot different than in the previous one, which was x plus 1/3 x cubed. You'll notice we do have both even and odd powers. That's because when we talk about that even-odd symmetry, we're talking about around 0. We're not going around 0 anymore. And if you go around pi fourths, it's not symmetric around pi fourths. So that's why it's not so strange to see both even and odd powers. Now, which polynomial is better? And the answer is it just depends where you want to be. If you're near pi fourths, this is our better polynomial. If you're near 0, then you go with the polynomial we did in number 1. All right. Number 3. Find the Taylor series for the function f of x, which is cosine squared of x cubed about x equals 0. Now, you might say, what can we do? Well, what do we know? We know the Taylor series for cosine. So the Taylor series for cosine says cosine of something is equal to the sum from 0 to infinity. And remember, the cosine, it's the one that alternates, and then what we have are the even powers. So something to the power 2k over 2k factorial. All right, so that's what our Taylor series for cosine looks like. And again, we come down and say, what's in the box? Now, the question is, what do we do? The tricky thing here is if we just had cosine of just x cubed, so there was not that square, then it would be straightforward. We say, well, what goes into the box? And the answer is, hey, just put x cubed in the box. But there's the square. Now, here's one idea, and let's think about it. Let's not rule it out quite yet. We can say, well, f of x, maybe I can think of this as cosine of x cubed quantity squared. So that would be what? Well, cosine of x cubed, I can put that rule in. That's the sum from 0 to infinity of minus 1 to the k, x cubed to the 2k, divide that by 2k factorial being squared. Which means that in theory, and it's an interesting theory, what I can do is I can just take that series, so that's x to the 6k over 2k factorial, and then I can just multiply it by itself. And if I were to do this, that would give me the correct answer, but I actually have to do this. And this equals somehow a sum from k equals 0 to infinity of some c sub k x to the k, right? So what we're after when we talk about a Taylor series, we're just saying a power series for that function. The tricky part is what happens here. And that's a tough one. That's a tough one. Now, sometimes you might say, well, what do we put in that step? Well, we could say, maybe a miracle occurs, and we're able to find what we want. And hopefully, well, all right. The answer is we will have something, but it's not necessarily something miraculous, because we're going to say let's dig deep into our knowledge of trig. So let's go back and take a step and say, what's making this hard? What's the part about this problem that we look at and we go like, ugh? Well, the answer is the square, because it's the part that we highlighted. Okay, so is there a way to get rid of the square? And now we think about our trig. So we say, wait a second, there's something called power reduction, which says cosine squared of something is what? Well, that's our 1 plus cosine of 2 something over 2. Where again, the something can be arbitrary. It doesn't really matter what it is. It could be theta, it could be beta, it could be eta, or it could be something that doesn't rhyme with any of those words. It just has to be something. So in our case, we could have it be x cubed. So, idea. We're going to use that power reduction to rewrite the function. So we're going to say, okay, we're really after the Taylor series, for not for the function written in this way, but for the function written using the power series reduction, which is 1 plus cosine of 2x cubed over 2. So we're going to think of that as 1/2 plus 1/2. And now, for the cosine of 2x cubed, I'll come up here, and what I'm putting into my box this time is 2x cubed. So that'll be a summation from 0 to infinity of minus 1 to the k, and then we're going to have 2x cubed, 2x cubed to the power 2k, and divide that by 2k factorial. All right, cool. So we're almost there. In fact, we're really close. If you clean this up a little bit, you say that's 1/2 plus, and now what we'll do is bring in this 1/2 here into the sum. So sum k equals 0 to infinity. We have minus 1 to the k. Here I have 2 to the power 2k, but then there's another 2 downstairs, so that makes it 2 to the power 2k minus 1. X cubed to the 2k breaks it to x to the 6k, and then we're going to divide by 2k factorial. Now, in some sense, this is a good answer, but there's one more small thing that we're going to do to help us, well, I don't want to say confuse ourselves, but to say, what were we really trying to accomplish? What are we after? So when we're thinking about writing a Taylor series, our real goal is we want to try to get powers together. Now, you might notice that there's a 1/2 here. What power does that attach itself to? Well, the answer is that it attaches itself to the 0th power. Well, is there a 0th power in here? And the answer is, well, yes. If you plug in 0, you get an x to the 0 power. So one thing you can do is you can say, well, let's think about pulling off just the first 0th power, because I want to put the 0th powers together. When you plug in 0, you're going to see you get a 0 here, a 0 factorial, which is 1 downstairs, and 2 to the minus 1. So you really get a 1/2 plus a 1/2 plus everything else. So everything else says starting at 1. Why? Because the key here is that this part right here, that's our k equals 0 term. So now we have 0, and then we start at 1 to infinity of minus 1 to the k, 2 to the power 2k minus 1, x to the power 6k, divide that all by 2k factorial. So we can combine these things together. And again, the reason that we're doing this is we just want to get all the coefficients of the same powers together. So we're going to get all our constants together. So 1 plus the summation k equals 1 to infinity of minus 1 to the k, 2 to the power 2k minus 1, x to the power 6k, divide that by 2k factorial. And there you go. That's the answer. Now, if you were to go up and come up here and do this process, if you were very, very careful, and I do mean very careful, and worked it out, we would be able to show this. But we'd have to do a lot of work to spot the pattern, and then even once we spotted it, we'd have to prove it. And so it wouldn't be a miracle, but it'd be a lot of hard work. And so it's better to say, look, let's avoid the hard work. Try to rewrite it in a more convenient way. A lot of math comes down to saying, if I don't like the way it's currently written, is there a way I can rewrite it that makes me happier? And if there is, let's do it. Well, all right. Good. That's number 3. Number 4. Find the Taylor series for the function f of x, which is 1 over 1 minus x minus 6x squared, centered at x equals 0. All right. Well, that's okay. Cool. Now, what do we do? Well, if there wasn't a minus 6x squared, this would be a super trivial problem. It'd be like so easy. We would be done before we even started. But of course, there is a minus 6x squared. But actually, this reminds us of something, which is the geometric series. So we're going to write that down for reference. So anytime you see a rational function, and recall that rational function means polynomial upstairs and downstairs, a lot of the time we're going to try to build off of geometric series. So we're going to recall. So we have 1 over 1 minus something. That's the sum from k equals 0 to infinity of something to the k power. Okay, so that's where we're going to be building off of. So our goal is to really get it very close to this form. And if we can get things into that form, then we're good. So with that in mind, we start thinking to ourselves, what do we want? And I should say, let's be really careful here. When I say I want something here, it's not just an arbitrary thing. So you might say, hey, I know what I could do. Maybe I could do this. I could say this is 1 over 1 minus x plus 6x squared. Well, isn't that the sum k equals 0 to infinity of x plus 6x squared to the k? Now, here's the thing I just want to make a note of. This is a true statement. It is true. It's not a flawed statement at all. This equals that. And for very small values of x, they actually do agree. However, what's the issue? That is not a power series. And in particular, if it's not a power series, it's not a Taylor series. So when we're doing a Taylor series, we really need to have it be something of the form x minus a to the k. And this does not have that right form, and therefore we can't just do that. So we got to be a little bit more careful. All right, well, if that doesn't work, what can work? Let's think about our function. I suspect that something nice must be happening. Oh, whoops. Why did I don't know why I forgot to shade the inside. There we go. I like those to be matched up. Okay, so we have our function f of x, which is 1 over 1 minus x minus 6x squared. And again, we can't just be like, let's pull out a minus. What can we do? Let's take a moment and factor everything that we've learned into answering what our next thing could be. When we factor all the tools that we've learned and factored all the problems that we've done and factor all the techniques that we've been using, what's something we can try? Yeah, we can factor, right? A lot of things factor. And do you think this factors? Well, let's try. If it were to factor, how would it factor? Well, the 1, there's not a lot of ways to write 1, so that would be 1 and 1. Now, 6x squared. Well, 6, you can break up as 1 and 5, 1 and 6. but there's no way to combine 1 and 6 together to get to 1. But you can combine it as 3 and 2. Okay, that seems promising. They differ just by an x. Now let's see, which one is it? Is it minus 3x plus 2x, or is it plus 3x minus 2x? Which one? Well, you can always try both. I think it's the minus and the plus here. Now, I say the word think, so that means I should check. So the 1, that's good. Plus 2x minus 3x, good. Minus x and minus 6x squared, we're safe. Now, you might say, okay, so it's a sum times a sum, right? Well, no. We're going to run the same problems as before if we think of it as a sum times a sum. So there must be something else we can do. Is there any techniques that we're somewhat partial to, things that we've learned in the past that can help us on these types of problems? And, something to help us when we have a fraction, perhaps. A partial to a fraction technique. Anything? Of course, you know where this is going. Partial fractions. So that, there's a great reason why we learned all this algebra. We learned all this algebra to be prepared to use it. Because the more algebra we can use, algebra is really about learning to rewrite expressions. And so that helps us. Because a lot of math is, how do I take my problem and rewrite it and make a simpler problem? And maybe if I make the problem simple enough, then life is good. So I start with my partial fractions decomposition. I clear my denominators. A times 1 plus 2x plus b times 1 minus 3x. Now I can expand and group, or I can plug in some nice choices. Do you see any nice choices we can make? Well, just think about what makes things 0. So for example, suppose I want to knock out the b. Is there a good choice for x? Well, I think if you choose x equals 1/3, that would be pretty good, because you get 1 minus 1, which is 0. So that says what? You get 1 equals a times 1 plus 2/3. Well, 1 plus 2/3. That's really the same as 3/3 plus 2/3 are 5/3 a. Or you could say a is 3/5. What if I want to knock out the a term? Well, choose x equals minus a half. Well, what does that give us? Well, now the a term is gone, so we get that 1 is equal to b, and then it's times 1 minus 3 times a half. Minus a half. Okay, there's a minus sign. Minus makes plus. Okay, there we go. So it's 1 plus 3 halves, 2 halves plus 3 halves, which would make this equal to 5 halves b. Or we could say that b is equal to 2/5. All right. Now let's return to our problem. So remember, what we're doing here on the side is rewriting our expression. So we get that this is equal to our a. So a is 3/5, so 3/5 times 1 minus 3x. 1 over 1 minus 3x. And then plus b, 2/5 times 1 over 1 plus 2x. Now, I'm thinking of my mold, so I'm going to write that 1 plus 2x downstairs as 1 minus 2x. So that way I can fit things into my mold. In the first case, I'm ready to go 3x. So we'll have 3/5 times the sum, k equals 0 to infinity of 3x to the k, plus 2/5, and now minus 2x, so that's going to become our sum, k equals 0 to infinity of minus 2x to the k. So what can we do? Well, we can really do some really easy manipulations, namely we can bring the 3/5 in, we can bring the 2/5 in, and we can even put them together because the sums start at the same place. They both really have an x to the k. So if we do that, we'll get the sum from 0 to infinity. Now from the first term, let's be careful. What do we have? We have a single 3 and a 3 to the k. So if we combine that together, that's 3 to the k plus 1 over 5. All right. Now here, we're going to get a plus. That minus, that's going to give us a minus 1 to the k. I have a 2 to the k and another 2, so that makes it 2 to the power k plus 1. Then I have that 5 downstairs, so that's also over 5. And then both terms had x to the k. And now we have our series. Now you might want to say, is it the right series? Is it really the Taylor series? And the answer is yes. Remember one of the statements we made a while back. If you find a series, it is the series. Because there aren't two different series that are going to approximate the function very well at 0. So any method to find a series is going to find the correct series that we need. So there we go. That's the answer to number 4. Ah, that one's fun. We got to do partial fractions. Woohoo! Good times. Good times. Number 5. Given that the function f of x is the sum from 0 to infinity, x minus 2 to the n over 4 to the n, find the Taylor series for f of x centered at x equals 3. Now that's kind of interesting. See, what this is saying here is if you look at this function, this is currently centered at 2. So what we're after is we say, let's take our function, which we're not really quite sure what it is, and let's shift it to 3. Now you might want to say, oh, maybe it's x minus 3 to the n over 4 to the n or something. Okay, I don't know. Well, we don't know yet, but we're going to get there. Now, how do we begin? Well, one way to begin is to think about what is our function? So let's think about how we've seen things that look like this before. Well, we say, that looks an awful lot like sum n equals 0 to infinity of x minus 2 over 4 to the nth power. So this is sort of a good idea, which is if you see things which are sort of geometrical in flavor, in other words, to the nth power, put all those pieces together. And this should hopefully be ringing a bell. Because, well, what does this look like? Well, it looks like a sum from 0 to infinity of something to the n. And we know one of our basic series says, oh, that pairs up with 1 over 1 minus something. You see, we've been going from this left-hand side to the right-hand side, but there's no reason why we can't go in the other direction. So if we say, aha, I recognize that, I've seen that before, I can go backwards. So we say, all right, what's in the box? Well, the answer of what's in the box is this x minus 2 over 4. So, all right, that's good. So what we can say is that our function then is equal to 1 over 1 minus x minus 2 over 4. Now, technically, this is just for a small neighborhood. That's okay for us for now. We're willing to accept that it's just for a small neighborhood. We're not going to be worried about issues of convergence. Well, let's clean that up. I'll multiply top and bottom by 4. And if we do that, we'll get 4 on the top over 4 minus x minus 2. And so that makes this equal to 4 over, and 4 minus minus 2 makes it 6 minus x. All right, so now what we've done is we said, this function that was given to us as a series, we can replace it by this expression 4 over 6 minus x. So that's how the function is behaving. And including, by the way, the function behaves like 4 over 6 minus x around x equals 3. The reason I can say that, in case you're wondering what's the justification, is if you come here and you ask the question, do I converge? In other words, is 3 in the interval of convergence? And it's safely within the interval of convergence. All right. But we're not done yet. Because now we said, okay, we're going to take this part and we're going to try to get back to a sum, but we want it not to be involving x minus 2. We want it to be involving x minus 3. So here's sort of our great So we're going to take a second here. So this is 4 over 6 minus, and I'm going to replace this by x minus 3. Now we've got to be careful here, because notice I've actually changed my function. So I'm not done yet, because I've got to correct this new piece I've added in. So that's a minus 3, so that's like I've added 3, so I'm going to subtract 3. You'll notice at the net effect is I haven't changed anything. Okay, or if you like, what is this? Well, this is really 4 over, and I can combine the 6 and the minus 3, 3 minus x minus 3. Now, we want to get to the place where it's 1 over 1 minus something. So what's our challenge? Well, we have a 4 upstairs, and we have a 3 down here. We would like these to be 1s. So what we'll do, that's easy enough for us to fix. We'll pull out a 4 from the top and a 3 from the bottom. From the top, we'll be left with 1, and from the bottom, we'll be left with 1 minus x minus 3 over 3. Because I want to fit my mold. And my mold says a 1 over a 1 minus stuff. So I want to make sure I get a 1 over a 1 minus stuff. So I'm pulling out the constants to let me do that. Now I fit my mold. So what does this become? Well, that's the sum from 0 to infinity. There's a 4/3 in front, because that's the 4/3 in front. And then this becomes a x minus 3 over 3 to the n. Now, how do we finish? Well, let's bring the 4/3 in. So we'll get the sum from 0 to infinity, 4 times x minus 3 to the n. That's upstairs. Downstairs, there's a 3 here, and then there's 3 to the n. And if we put those together, that means there's n plus 1 3s, or 3 to the n plus 1. And now that is the series that we want. So this is kind of a fun one where we got to sort of jump around. So we jumped from our power series to a function, manipulated that function, and jumped back to a different power series. But at the end, I mean, no one single step is too bad. At least I hope not. So, all right, cool. Okay, that's number 5. Number 6. All right, given that f of x is sine of x cubed e to the power 3x, find the 10th derivative at 0. Aha! Aha! Interesting. Now, you might say, there's a good plan for that. And remember, what's our good plan? When I'm looking for a high order derivative, I say, well, wait a second, this function f of x, we can really approximate this. See, f of x, we're going to think of that as the sum from 0 to infinity, our kth derivative, evaluated at 0, and then we're going to times that by x to the k, and I'm going to go ahead and put the k factorial attached to there. So that's what the function f of x is. And I say, the 10th derivative at 0 is showing up in here. And in particular, if I look at the coefficient, not just any coefficient, because there's, infinitely many, but if I look at the coefficient of x to the 10th, this becomes the 10th derivative at 0 over 10 factorial. So, we have an idea. In some sense, what I want to do is I want to figure out what's the power series here, and what's the coefficient of x to the 10th. What's the problem? Well, certainly it's not a problem to find the power series for sine of x cubed. We'll get to that in a second. And it's not a problem to get the power series for e to the 3x. The problem comes from how do you find the power series for both of them put together. So let's start with the individual pieces. So first off, sine of something, That's the sum from 0 to infinity. And sine, it's one of the ones that has the alternating, and the sine is the one that does the odd power. So something to the something to the 2k plus 1 or 2k plus 1 factorial. And while we're at it, the e to the something, that's our sum from 0 to infinity, and it's just something to the k over k factorial. All right, so we just got to figure out what our pieces are, and for us, there's really no surprises. We know what our pieces are that are being plugged into our function. That's being told to us. So let's get to work. We have that sine of x cubed e to the x is equal to, well, the first one, that's the sum k equals 0 to infinity of minus 1 to the k, x cubed to the power 2k plus 1, divide that by 2k plus 1 factorial. Now e to the x will be what? Well, that'll be, whoops, e to the 3x. Sorry about that. I almost missed that 3. E to the 3x will be the sum k equals 0 to infinity of 3x to the k over k factorial. Now, there isn't some really cool fancy identity that's going to let us put these things together in a nice way. And so at this point, you might be thinking, all right, we're toast on this problem. Oh, we're not going to be able to solve it. And we were so close, we'd gone so far. Let's not give up though. Let's start by thinking about what's happening. So what's happening is I have two polynomials multiplying together. And the way you do two polynomials multiplying together is you multiply it piece by piece. Now, if I want to end up with the coefficient of x to the 10th, I have to multiply a piece from here by a piece in there so that the powers combine together to give me x to the 10th. Now let's look at the first couple of pieces here. So what would the first piece be? K equals 0. Well, it would be a plus x cubed to the 1, so that's x cubed over 1 factorial. So you get an x cubed. Now, what's the next term? A minus, then it's going to be x cubed to the 3, so that's x to the 9th, over 3 factorial. So that's minus x to the 9th over 3 factorial, which is 6. Now, what's the next term? This is important here. The next term will be, it'll be when k equals 2, it'll be x cubed to the 5, which is x to the 15th. Notice if I multiply something by x to the 15th, it's going to be bigger than x to the 10th. So, what's going to happen is that when we multiply these together, these two pieces are the only terms from the first part which can contribute to x to the 10th. So everything else will not be able to contribute to the x to the 10th powers. All right, well that's good news for us. So how is it good news for us? Well, we have to think, what do we need to multiply by? So if I'm multiplying x cubed here, x cubed times x to what power gives me x to the 10th? So the answer is x to the 7th. And I'll come back to here in a second. If I'm multiplying x to the 9th, x to the 9th times x to what power gives me x to the 10th? And the answer is the x. And I'll come back to there in a second. So what I care about is in the second series, I don't need to know very many pieces because when I'm multiplying, I always combine. So the question is, how do I combine? Well, the x cubed will combine with the x to the 7th. The x to the 9th will combine with x. So let's talk about the x to the 7th term. What would I have? Well, that would be when k equals 7. So that would give you a 3 to the 7th, divide that by 7 factorial, right? Because you have 3 to the 7, 7 factorial. When x equals 1, what do we have? 3 to the 1 divided by 1 factorial, which is 3. So we have a 3x, a 3 to the 7th over 7 factorial, x to the 7th, and then lots of other stuff, but this is the important idea. No other pieces are going to be useful. So these are the only parts from the second pieces that we need to care about. So another way to say it is these are the only parts which can combine with the first part and get x to the 10th. So when we multiply these together, what will we end up with? Well, we have x cubed times x to the 7th. The coefficient of that will be, all right, this equals, there's a lot of powers before the 10th power plus something x to the 10th plus other things. So we're going to have the x cubed times x to the 7th, we'll have the coefficient will be 3 to the 7th over 7 factorial. And then we're going to have the x to the 9th times the x, so that's minus 1 over 6 times 3, which is also known as, 3 over 6, or you can write that as a half. If you wanted to, you could. Okay, so the story is we've now found the coefficient of x to the 10th. It's right there in front of us. So this part is our coefficient of x to the 10th. Now, this is not our answer. Even though I've boxed it, it's an important part to get to our answer. Because the other thing is say, hey, this is also the coefficient of x to the 10th. So we now put these two pieces of information together. And we can conclude that the 10th derivative at 0, divide that by 10 factorial, is equal to 3 to the 7th over 7 factorial minus 3 over 6. And now, if I just want the 10th derivative, I just have to move the 10 factorial across. So the 10th derivative, evaluated at 0, is 3 to the 7th over 7 factorial minus 3 over 6. And that is all multiplied by 10 factorial. And that is the answer. Ah, wow, that's kind of cool. And it's not so obvious that you can get to it right away. This is dealing with a very particular topic that we mentioned once. And if you're interested in what this is called convolution. So convolution shows up whenever you're trying to combine two different series together via multiplication. And that's the process that you can put things together. All right, well, number 7. So, rewrite the sum k equals 0 to infinity of minus 1 to the k, x to 2k plus 1 over 2k plus 1 factorial, sum k equals 0 to infinity, minus 1 to the k, x to 2k over 2k factorial, as a single series. So this is getting back to the convolution. Now, if you look at our last problem that we just did with convolution, you're going to be like, this sounds tough. And if you were to do it as written, it would be tough. But before we do it as written, let's think about, are these random series? Or have we seen something like this before? And I think if I'm asking that question, the answer is we've seen something like this before. Yes, we have seen something like this before. Do you remember what they are? Well, these are the sines and the cosines. Remember, sine of something, that's the sum from 0 to infinity of minus 1 to the k, something to the power 2k plus 1 over 2k plus 1 factorial. And the cosine of something, because sine is odd function, odd powers. Cosine, very similar. It just has, instead of the odd powers, it does the even powers. So we say, hey, hold on. These aren't just two random series. that we're multiplying together. These are series with a history that we've gone back with over a very long time. So we can say, let's not think about multiplying the series together per se. Let's say we know that this part is really sine times cosine. Now, what's the ideal situation for us? The ideal situation for us is to take these two things and write them as a single function. So in other words, we really like to get down to just sort of a single x. One x to rule them all. One x to find them. One x to bring them all. And in the light of calculus, bind them so that we can solve it. So sine x times cosine x, have we ever seen something like that? Is there some trig identity that we might know? It's time for us to double down on our trig. Do you remember the right identity? It is the double angle identity. Sine of 2x is 2 sine of x cosine of x. So we see that this is really 1/2 sine of 2x. So now we can use our blanket formula for sine. See, we saw this was sine of just x. We're just going to replace the inside now by 2x. So we get 1/2 times the sum from 0 to infinity minus 1 to the k of 2x to the power 2k plus 1. And then we're going to divide that by 2k plus 1 factorial. Well, let's clean that up. So this is a half. Sum k equals 0 to infinity, minus 1 to the k, 2 to the power 2k plus 1, x to the power 2k plus 1, and divide that by 2k plus 1 factorial. Now you see that half? We can multiply it in, and you'll notice that that's really like a 2 to the minus 1. So this half will knock out that plus 1. So we have 2 to the 2k. Now 2 to the 2k is the same as 4 to the k. And that means we can combine those two together. So, little side note here. So minus 1 to the k, 2 to the power 2k. It's like minus 1 to the k, 2 to the 2 to the k. So that's minus 1 to the k, 4 to the k, which is minus 4 to the k. So that's the computation that we're doing. So we get the sum from 0 to infinity of minus 4 to the k power x to the power 2k plus 1. Divide that by 2k plus 1 factorial. And that's the answer. Ah, cool. So this is, again, it looked like a hard problem. If we were going to try to do it directly, it would take a lot of work. But this is a, do you learn to recognize things? That's why we want to memorize our basic handful of formulas, because there's only a handful of things that we can learn. And if we can start to say, oh, that looks like this, that looks like that, that gives us power. And the more power that we have, the better off that we'll be. All right, number 8. Find the exact value of the sum n equals 1 to infinity of negative 1 to the n over n to the 3n. Now, this gets us back to problems where it says, find the exact value. We've said that there's 3 ways to do this, and we talked about them before. And we said, well, they are geometric, we can find the exact value for. There's telescoping, we can find the exact value for. And then we said, well, there's a third one which we won't talk about for a couple weeks. It's been a couple weeks. So the last thing is Taylor series. So these are, whenever you see a problem that says find the exact value, it's going to be one or more of these 3 ideas coming into play. Now, of course, the real question is, which one of these 3 ideas do we need? It's probably not telescoping, because telescoping says I can break it up where it's like, something with an n plus 1 minus something with an n. This doesn't have that flavor. Is it geometric, and why not? Well, it's not geometric. The reason it's not geometric is because of this n here. When we have something that's geometric, we should have it as something to an nth power, so a constant to the n. The fact that there's this extra n floating here means this is not a geometric series, which means this is a Taylor series. So we need to start thinking and putting on our hats of saying, do we recognize this Taylor series? And if we don't, can we figure out what it is? So I don't know if this is so obvious from the start. So we're going to put on our thinking hats. Now here's sort of a strategy. So I'll write down strategy. What we want to do is think of this as a Taylor series. And how do you think of this as a Taylor series? And the way to do it is to do the following. And what you have is, if you see something to the n, make that as x to the n. So in other words, I want to think of it as there's a variable involved. Now the way that variables show up in our Taylor series is as like x to the n. And so I say, oh, if I see something to the n, I'll think of that as x to the n. So right now I'm going to say, let's suppose I looked at the sum n equals 1 to infinity. I have negative 1 to the n, 3 to the n, and so this currently, I'll do a little note here, this is sum n equals 1 to infinity as 1 over n times minus a third to the n. So I'm going to think of this as 1 over n x to the n. Okay? So what's the thought process again? The thought process is, again, if I want to think of it as a Taylor series, I need to get an x to the n. So I'm looking for something to the n. And in this case, the something was the minus a third. All right. Now we look at this and say, okay, suppose this was our starting point. Can I make this look like one of the series that I'm comfortable with? And how do I go about doing that? Well, you can make it look like one of the series that you're comfortable with, because this looks really close to just x to the n. Let's give this a name for right now. We'll call this, for lack of a better name, f of x. I would like to get rid of that 1 over n, and the way I can do it is take a derivative. So f prime of x would be the sum n equals 1 to infinity of 1 over n, and then the n comes down x to the power n minus 1, which is the sum n equals 1 to infinity of x to the n minus 1. Now this might not look so familiar, but be careful here. We started with 1. So what's our first power? X to what power? It's x to the 0. So this is 1 plus, when you plug in n equals 2, x to the 1 plus x squared plus x cubed plus, this is the geometric series. This is 1 over 1 minus x. So the derivative of our function that we're trying to understand is 1 over 1 minus x. So if we take the antiderivative, what will we have? Well, we'll have f of x. The antiderivative of 1 over 1 minus x, that's equal to minus natural log of 1 minus x, and of course that's plus c. All right, so that's what goes up here. So we have that the sum from 1 to infinity of 1 over n x to the n is minus the natural log of 1 minus x plus c. How do you get the plus c? Well, we're going to choose. But, of course, we're going to choose wisely. So by choosing wisely, we're going to plug in something which is nice. For this side, the nice thing is 0. So plug in 0, and what do we get? We get that 0 equals 0 plus c, so that tells us c equals 0. So we're almost there. We're almost there. Okay, if you survive this far, then it's just like a, oh, to finish it off. So at this stage we have that the sum from 1 to infinity of 1 over n x to the n is minus natural log of 1 minus x. Remember we said think of it as whatever to the n, we replace that something by the x. So to get back to where we have, now plug in our x equals negative 1/3. So our sum from 1 to infinity of 1 over n minus 1/3 to the n is equal to minus log of 1 minus 1/3. Well, minus, two wrongs make a right. So minus natural log 1 plus 1/3 is 4/3. Now here's something you can do which is fun. Remember we have that minus in front. We can bring it in as an exponent. And really that minus just means flip the inside over. And so if you flip 4/3 over, you get 3/4. And that is the answer. So that's the exact value of that sum, is this natural log of 3/4. And we did it by thinking, okay, we had to think of Taylor series. We figured out what the right Taylor series for it was, and then we did the correct evaluation. All right. Number 9. Okay. Find the exact value of the following sum. E to the n plus n factorial. Divide that by e to the n times n factorial. So the top and the bottom, they both involve e to the n and n factorial. Upstairs we add, downstairs we multiply. When we put this all together, what will we get? What will we get? Well, there's good news, namely that upstairs addition, this is the good place to put addition. We love addition upstairs. It's our favorite thing. Why? Because it says, hey, I can pull this apart into 2 separate pieces. And so oftentimes it helps us to pull things apart. So sum n equals 0 to infinity of e to the n over e to the n times n factorial. Okay, that's the first piece, plus sum n equals 0 to infinity of n factorial over e to the n times n factorial. That's the second piece. Now we say, oh, well, in our 2 pieces, we get different cancellations. So, what do we have? Well, this is the sum n equals 0 to infinity of 1 over n factorial plus the sum n equals 0 to infinity of 1 over e to the n. And I can write that as 1 over e to the n, so in that form here. Now, one of these series is pretty straightforward, and the other one is also relatively straightforward if you have the right way to see it. Now, among the two, the one that we should be able to think of almost automatically is the second one. This is geometric. How do I see that it's geometric? Well, the key is to note it's something to the n. So the fact that we have that exponent there to the nth power of a constant, that's what tells us geometric. So, according to that, we get 1 over 1 minus, now the reason we have a 1 up here is n equals 0, the first term is 1. 1 minus what we multiply by, 1 over e. Now, if you multiply top and bottom by e, you get e divided by e minus 1. Okay, so that is the second term. Well, okay, how about the first term? Well, this is not geometric because it's not to a power n. It's not telescoping. So that means that if we were looking for the exact value, and we are, then we're not doing telescope and we're not doing geometric, so we need to start thinking Taylor series. All right, so we start rummaging through our mind and thinking, is there a Taylor series that involves an n factorial? Well, there is, and it's the function e to the something is equal to the sum of n equals 0 to infinity, something to the n over n factorial. All right, well that's good news for us. Now the only question is, how do we get from this to there? Well, it's like I don't want anything up there. I don't want something to the n. I just want 1. Well, is there something I can plug in where something to the n always gives me 1? And the answer is, yeah, plug in x equals 1. So we're going to put our something equals 1, and what do we get? Well, what we get is that e to the 1 is equal to the sum of 1 over n factorial. So that is e. Okay, so we're not quite done yet. We've got to simplify. So we have e plus e over e minus 1. Common denominator, e times e minus 1 plus e all over e minus 1, which is e squared minus e plus e. Divide that by e minus 1. The e's cancel, and we're left with e squared. Divide that by e minus 1. And that's our exact value. That's fun. In fact, this came from a final exam from a couple of years ago. It was a really fun problem. Some students loved it, and some students loved it a little bit less. But when you see it, I think it's beautiful, because there's sort of this idea of like, oh, I'm trying to find an exact value, and I'm going to do two ideas, geometric and Taylor, and things come together in a nice, beautiful symphony to give us our final answer. Which brings us to number 10, our last problem on our last quiz. It's been a long journey. Well, I hope it's been worth it. Let's make it a good one. Use the first three non-zero terms of the Taylor series of the square root of 1 plus x cubed to estimate the integral from 0 to 1 of the square root of 1 plus x cubed dx. Now, technically, I should say there's a small snafu, a small glitch in this problem, which is we haven't said centered where. So we'll put that in. Centered at x equals 0. Okay. Shh, don't tell anybody. I forgot to put that in. All right, it's just between us, our friends. Now, the square root of 1 plus x cubed, what kind of series is that? It's not e to the x, it's not sine, it's not cosine, it's not geometric. Do you know what it is? It's binomial. So let's write down our binomial series. So our binomial series says 1 plus z to the alpha is equal to the sum, k equals 0 to infinity, of alpha choose k, z to the k. Now, of course, I put z. In the past, I've been putting in a little box. See, this is just a stand-in. It says, well, what's the something? Now, all right, what's our case? Well, our case is we have the square root of 1 plus x cubed. So what we can do is we can say the following. The square root of 1 plus x cubed, that's really like 1 plus x cubed to the 1/2. Now, the pieces are, this 1/2 is alpha, and the x cubed, this is our z. So, that's how we fit into here. We get that this is equal to the sum from 0 to infinity of 1/2 choose k times x cubed to the k. So that's x to the 3k. Now, we want to do the first three non-zero. So let's start our terms. K equals 0. By convention, whenever we have something choose 0, it's going to be 1. X to the 0 is going to be 1. So 1. So this is our K equals 0. Then 1/2 choose 1. So, well, we'll go ahead and write that as 1/2 choose 1. X to the 3. This is K equals 1. And then 1/2 choose 2. X to the 6. This is K equals 2. And plus ... We're only going to grab these terms. Let's clean that up. So that's 1. 1/2 choose 1. Well, what that'll be is you're going to start with the half upstairs, 1 downstairs, and then we're going to make sure we have one term on both top and bottom. Well, we do. So that's it. Oh, that was quick. Plus the 1/2 choose 2. I'm going to start with the half upstairs, 2 downstairs, but I need 2 terms on the top and bottom. So 2, 1. Upstairs will be half and minus a half, because we're going to go down, subtract 1 each time. X 6 and ... So we end up with 1 plus 1/2 x cubed, and then a 2 and a 2 and another 2. So that's a minus 1/8 x to the 6. All right. That's our approximation. So, well, I should say that's actually our sum. So here, this part right here, this is what we're going to use to do our approximation. So we're going to say our function square root of 1 plus x cubed is behaving like this function here. Now, what does that tell us? Well, what that tells us is that the integral from 0 to 1 of the square root of 1 plus x cubed dx is equal integral 0 to 1 of, I'm going to replace it by my approximation. So not equal, approximate, 1 plus 1/2 x cubed minus 1/8 x to the, 6. I'm getting excited because I know what's coming, dx. Now we integrate. So we're going to get x plus, so we have 1/2, and then we have x to the 4th over 4, so that's going to be 1/8 x to the 4 minus, here I have an 8th, then I'm going to get x to the 7 over 7, so that'll be 1/56 x to the 7. And then we're going to evaluate that from 0 to 1. Now the nice thing is when you plug in x equals 0, you get 0. When you plug in 1, you get 1 plus 1/8 minus 1/56. Well, that's 56 over 56. And then 8, well, what did you have to multiply 8 by to get 56? The answer is 7. So plus 7 over 56. And then minus 1/56. Well, that's 56 plus 7 is 63. Subtract 1 gets you to 62 over 56. They're both even numbers. So if you divide, that's 31 over 28. And that is the approximation that we wanted. Our final answer on the final problem of our final quiz. Oh, it's hard to believe it's coming to an end. It's been so much fun. And, well, the math never has to end. We still get more review problems, chances to talk, the final, and there's always Calc 3, right? So the fun goes on. I want to say, since this is near the end, thank you. Thank you for coming, for watching, for being patient, and for giving. You know, we're trying, and I hope that you're doing okay. We want you to do okay. We want you to be happy, healthy, physically and mentally, and we hope you're doing well. And so with a lot of love, and truly we do care about you. We want you to succeed. We hope you're doing well. And if you need anything, let us know. All right, my dear friends. Goodbye.